What is the difference between binary decimal and hexadecimal numbers? So first off, I'm going to take you to the end of the video. The end of the video, I'm going to show you how all this ties together with what's called an Arduino Uno. And right here you can see the Uno. Let me kind of move it so you can see it. So this is a RGB light and 3 resistors and the wiring to the Uno. And here's what the code looks like. There's 3 numbers that do red, green, and blue. And if you hit the start simulation, the program runs. So I'll get rid of the code, and you can see here that that's the numbers I plugged in there gives it a yellow color. And if you stop the simulation, the electricity shuts off and there's no color. So I'll just show you how hexadecimal numbers relate to that. So the first thing we need to start with is the decimal number system. It's the number system you're familiar with. You know, you learned how to count when you're a little baby, probably just barely able to talk. Your parents are already teaching you how to count your fingers and toes and things like that. Well, if you think about the decimal number system, we only have 10 symbols. And those 10 symbols create our entire system. And, you know, these are dominoes. So here's 0 things. Here's 1 thing. Here's 2 things. I love the fact that numbers are just an adjective describing these 3 dots. 3 dots. So it's an adjective describing a noun. 5, 6, 7, 8, 9. Our problem we run into is what happens when we have these numbers. We're above our symbols. Well, then we got to talk about place value. And so how I like to think about, you take this for granted. It's the number 10, duh. But a lot of times you've kind of memorized that. You don't really think about what it takes to make that. And so the number 10 is really one set of 10 things plus 0 things. And so that allows us, that's a very powerful thing. That allows us to describe numbers that can be infinitely larger. So, how do we represent this number in base 10? Well, this is a 5 by 5 set of dots, so this is 25 dots. You think, oh yes, it's 25. Well, if you think about this, what we have is we have 2 sets of 10. So there's a set of 10, there's a set of 10, and then these 5 dots. So 2 times 10 plus 5 is really how we look at this in base 10, or 25, because 2 times 10 is 20, plus the 5 dots that aren't base 10. So that's the fundamental part of it. And so let's say, so what we really have is with place value, you have to think of it in how many 10s we have. This is the units place. Okay, the units place has 10 to the 0 as a multiple. So 10 to the 0 is 1. So this would be 10 to the first power, this would be 10 to the second power, and this would be 10 to the third power. Or 1,000. So we've got 1,000, 100, 10, and 1. And so all of these numbers up here, if I fill those in, and let's say we do this number here, 2,347, there we have 4 place values. Again, this is 10 to the 0 because we have 10 symbols, so we can't go above that number. 4 is 10 to the first powers. We have 3 10 to the second powers, and we have 2 10 to the third powers. And so you can look at it in expanded form like this: 2 to the third, 2 times 10 to the third, plus 3 times 10 squared, plus 4 times 10 to the first, plus 7 times 10 to the 0. Or 2,000, because 10 to the third is 1,000, plus 300, plus 40, plus 7. So 2,347 if you added those together. Now, you might think, well, yeah, I learned that when I was in 4th grade or 5th grade or 2nd grade, I don't know, whatever grade you're in. But that is fundamental for the other bases. So you have to understand how to expand these. And so let's look at binomials next. I said binomials, I meant binary. That's a math teacher brain freeze there. But binaries have two symbols. You have a 0 or a 1, and that is it. That is all the numbers you can use in a binary system. And so with two symbols, like base 10 has 0 to 9, that's 10 symbols. With binary, we only have two symbols. And so this could stand for true or false. Well, and I'm doing that wrong. You know, 0 represents false in a computer. 1 represents true. On represents 1. Off represents 0. Power, no power. That's essentially why that we use the binary system, because it's just, your computer is just a set of, trillions of switches. And so with only two symbols, and that's how they have to communicate, we have to create all of our language, everything, our color, everything we do in the world is really, a computer sees it as two numbers, either a 0 or a 1. Is it on or is it off? That's all it can think about. And so we have to come up with a way that we can interact with the computer, and that's where we'll talk about hexadecimals. But let's understand what a binary is. So if we counted, the first number would be 0 or nothing. The next number would be 1. Well, now we're already out of numbers. So we have to have another place value. So your next number is 1, 0. That is the number 2 in base 10. And I'll explain this in a second. 1, 1 is the number 3 in base 10. Well, we're out of symbols again. So to get 4, we've got to go 1, 0, 0. That's 4 in base 10. I'm putting a little 10 there so we know it's base 10. Maybe you could put an equal sign. 1, 0, 1 is 5 in base 10. 1, 1, 1, or 1, 1, 0, excuse me, is 6 in base 10. I almost messed up there. 1, 1, 1 is 7 in base 10. And now we're out of numbers again, and we get to what's called a nibble. So 4 digits in binary is called a nibble. So now we have the number 8. And the largest number we could represent with a nibble is the number 1, 1, 1, 1. And let's talk about this now. So in base 10, remember it was 10 to the 0 for the units place. Well, with base 2, it's 2 to the 0 for that first digit. And in here, this would be 2 to the first, this would be 2 to the second, and this would be 2 to the third. So this number could be expanded out as 1 times 2 to the third, plus 1 times 2 to the second, plus 1 times 2 to the first, plus 1 times 2 to the 0. Well, if we do that, that's 8, because 2 to the third is 8, times 1 is 8, plus 4, plus 2, plus 1. Well, if we add all those up, 8, 9, 10, 11, 12, 13, 14, 15. So 1, 1, 1, 1 is the largest number we can represent with a nibble. That's 4 binary numbers put together. Now, one thing I did skip on there, I forgot all about it, but these two are called bits. It's either an on or an off. We call that a bit. Okay, a nibble's when we put 4 of those bits together. And then if we go ahead and combine 2 nibbles, so 1, 2, 3, 4, 1, 2, 3, 4, this is now a byte. So a byte is 8 digits in binary. And what's special about a byte is we can we can have a total of 256 things represented with a byte of data. And that's going to, that's just what they decided on way back in the day, probably in the 70s and probably before the 70s, probably right in the 70s and 80s. But 256 things is a byte, and we're going to have numbers that look something like this. We'll say we had 101101. Okay, so that number represents, in base 10, let's go ahead and convert it. This would be 1 times 2 to the 7th plus 0 times 2 to the 6th plus 1 times 2 to the 5th, or sorry, yeah, yep, that's right, plus 0 times 2 to the 4th plus 1 times 2 to the 3rd plus 1 times 2 to the 2nd plus 0, and I'm out of room, so plus 0 times 2 to the 1 plus 1 times 2 to the 0. And I ran out of room again. And if you add that all up, we'd have 128 plus 0 plus 32 plus 0 plus 8 plus 4 plus 0 plus 1, because 1, this would be 1 times 2 to the 0. And if you add all those together, you get 173. So 10101101 is 173 in base 10. You might think, well, who cares? Well, if you go into our program and go into our code, I can actually change my color. Instead of 255, I can change that red value to 173. And when I hit the start simulation, we get should get a slightly different shade of yellow there. It's taken a minute to initialize. Yep. There we go. Now it's going. Yeah, it's a slightly different shade of yellow. It's not as bright because I took some of the red out of it. And so so it changes. Every one of those numbers changes inside that simulation based on the number I produce. So that is binary. So what about hexadecimal? So in a red, green, blue light, you need 3 bytes of data. So 3 bytes of data to run to produce one color. And so 3 bytes means we have to have, so if we wanted this color, so here's 1. So if we want 1 1 1 1 1 1 1 2 3 4 5 6 7 8, and then 8 zeros, 1 2 3 4 5 6 7 8, and then 1 2 3 4 5 6 7 8. Okay, this is the number that the computer's reading for red. This is green, so it's saying 0 green and 0 blue. So 3 bytes of data, that just runs 1 pixel on your screen, 1 color. So it just produced red, and 1 little spot you'll have a hard time even seeing on these new modern screens that we run. And so imagine programming that for the thousands and tens of thousands of pixels on your screen. If you had to speak computer, that's how you'd have to do it. If you wanted, say blue and green, which is the color yellow, blue and green, the color yellow would look like this. Or red and green, red and green. So 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. And now you've got red, green, and 0 blue. So you've produced the color yellow. And so it gets kind of cumbersome to have to communicate in binomial. But that's how your computer has to communicate. It's just a series of on and offs. And so we have this nice transition thing, which is hexadecimal, and it's still used. If you look on most of your RGB stuff, RGB red, green, blue, if you look up RGB color codes, you're going to find this hexadecimal. Most of the codes will be in hexadecimal, which is kind of neat. So hexadecimal is a base 16. So base 16. So there are 16 symbols in hexadecimal, and they start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But we're not to 16 yet. So you've got A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. So there's your 16 symbols in a base 16 system. So a number in base 16 might look like this, AE. Okay, so that's a number? Well, yes, it is. So A, if you remember from my symbols before, A represents 10, B represents 11 in base 10, C represents 12, D is 13, E is 14, and F is 15. There's my 16 symbols, but remember, these are all base 10 up here. And so what you have with this, for some reason it's not letting me switch to the next. We have AE, we just have a 2-digit number. Well, this is base 16 with 16 symbols, so E is times 16 to the 0, and A is times 16 to the 1. And so what you have then, A represents 10, so if we're going to convert this to base 10, you would have A times 16 to the first power plus E times 16 to the 0 power. Well, A is in base 10 is 10, so 10 times 16 plus E is 14 times 1, because 16 to the 0 is 1. So we'd have 160 plus 14, which if you add those two together, you get 174. Now, what's cool about this is A is 10. And if you go back to, let's just look at that AE. So we know that's 174 in base 10. This is base 16. So let's backtrack it to binary. And what's cool is A is 10. Well, that's a byte, that's a nibble of information, A is. And E is a nibble of information. So if you can represent A, which is 10, and E, which is 14, if we can represent those in binary. So A is 1010, and E is 1110. So if you check this out, remember this is 20, 21, 22, 23. So this is 8 plus 2, which is 10, which we have. And this E is same thing, 2 to the third, 2 to the second, 2 to the first, 2 to the 0. That'd be 8 plus 4 plus 2, which gives you 14. Okay, so just translating the A and the E gives us the entire string. And what's cool is if you start it from the beginning, and maybe this is confusing, but I was just blown away by this when I first learned it. 10101110, if you take it as an entire byte of information, that is, this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third. Then you'd have, instead of 2 to the 0, that'd be 2 to the fourth, 2 to the fifth, 2 to the sixth, and 2 to the seventh. Well, 1 times 2 to the seventh is 128, plus 0 times 2 to the sixth is 0. 1 times 2 to the fifth is 32. 0 times 2 to the 4th is 0, which is 2 to the 4th is 16. 1 times 2 to the 3rd is 8. 1 times 2 to the 2nd is 4. Plus, and then plus 2 to the 1st. 1 times 2 to the 1st. And if you add all those up, you get 174. So you don't have to go do what I just did, but I'm just showing you that it works. If you just simply translate the A and the E, you get your two nibbles of information, and it creates the entire number. So it's way easier to deal with programming-wise. Okay, and so maybe we should do we're getting to 20-minute video, so maybe we should do some actual colors. And so what's kind of cool is if you go to random.org, so random.org is a great site, and it generates colors for us. So I'm generating just random colors. So those are all in hex values, and those are the colors of those hex values. So let's go ahead and translate maybe that last one there and see what we have. So let's go ahead and program that 9F, 8F, 3D. So 9F, you've got two digits. This is 16 to the 0, and this is 16 to the 1. So that would be 9 times 16 plus 15, because that's what the letter F represents, is 15, times 1. Well, 9 times 16 is 144, plus 15 is 159. So this number is what we'll use to program in for our color red. So that's how much red we'll put into the color. 8F, again, same thing, 16 to the 1, 16 to the 0. That's 8 times 16 plus 15 times 16. And that would be 128 plus 15, which is 143. And so this is our green color we'll program in. And then 3D, that is 3 times 16 to the 1st, plus D is 13. I had to look that up because I wasn't paying attention. 13 times 16 to the 0. So 3 times 16 is 48, plus 13 is 61. So if we go ahead and program in 159, 143, and 61, we should be able to generate that color. So I've still got my program running from the last time. We'll stop simulation, go to the code, and change the red value to 159, change the green value to 143, and change the blue value to 61 and see what we get for a color here. So we'll start simulation, hide it, and that doesn't look like the same color, does it? Looks a little different. So I'm wondering if I've got a wire crossed. So this happens all the time in wiring. So let's switch these out. Let's change this over to here. Whoops. Let me escape. Let me pause this, and I'll show you so I don't take up any more of your time. So I changed two wires. I changed the blue one. I switched it to go to here, and the green one to go to here. And so I must have had an issue with my blue and green wire. I must have had those crossed. So let's start the simulation again. Yeah, and see there we get the color we were looking for. So if we look, we go back, there it is, that kind of, we call that in Nebraska, we call that calf scours. But that's the color I'm producing with my circuit now finally. It's not exactly exactly the same, but it's dang close. So I just had to switch those, and that happens. I mean, that's part of when you're coding and you're doing this stuff. Sometimes you get your wires crossed, and that's what's fun about the whole thing. So that's my video on converting to hex and binary and decimals and how important they are to programming. And so I hope you learned something. I hope it helps, and I'll see you next time.